Today's lesson is on zeros and multiplicity. The next couple of lessons for Unit 8 are lessons that are leading us up to graphing polynomials, so it's all the key aspects we need in order to put the function on the graph. So right here at the top it says the terms of a polynomial are in descending order by degree. The degrees decrease from left to right. This order demonstrates the standard form of a polynomial, which hopefully at this point everyone is familiar with. We've been doing it a lot. A couple of key things to point out is your leading coefficient. That term is always going to be important. And I generally abbreviate leading coefficient as LC in my notes just to save the time of writing out that word. It's also important to recognize the degree of the function. The degree is the largest exponent. And when I say largest exponent, it's the largest exponent of the entire function. You have an exponent of 3, 2, 1, and then no exponent. So the largest one is 3. That's considered the overall degree of the function. All right, before we start the notes, there's a warm-up which I would like you to do by yourself. I did include my answers here. I'll briefly discuss them, but I want to make sure everyone is all set with factoring. So factoring is actually what we've been doing the last 2 days. Hopefully everyone feels confident in their factoring methods and how to solve. So I'll leave my answers up here for a minute while you work through them, but just to, talk about the first one here. So for number 1, we have f of x is equal to x cubed minus 6x squared minus 27. Don't forget that you always check for a GCF, of which number 1 has. So you take out the GCF, you factor, you end up with what we call the factored form. So be very careful, understand the difference. It's why I labeled these. You have your factored form, and then from your factored form, you set each one of your factors equal to 0. And when you do that, you end up with 3 solutions. You have a solution of x equals 0, a solution of x equals negative 3, and a solution of x equals 9. So you set each one of those equal to 0. Okay, take a moment and complete these 2 factoring problems. Make sure you get the same answer as me, especially on number 2. And we'll go over the remaining set of notes in just a moment. Standard form versus factored form. Always a big deal. Sometimes we forget how to go back and forth between the two of them. So let's start at standard form and let's work our way to factored form, and then we'll do it the other way around once we finish. So for this one, we have x cubed minus 2x squared minus 15x. If I want to factor this, I'm going to recognize that I have a GCF of x. So I can factor a GCF of x out, leaving me with x squared minus 2x minus 15. And then I'm going to look at this expression here, and I'm going to think to myself, what 2 factors multiply to equal negative 15, and the same 2 factors that add to equal negative 2? That's going to be negative 5 and positive 3. So I can rewrite this as x multiplied by x squared minus 5x plus 3x minus 15. And at this point, all I did was rewrite negative 2x as negative 5x plus 3x. To factor, I'm going to group the first 2 terms and the second 2 terms. For the next step, we have our GCF of x multiplied by the GCF of the first group is x, left over x minus 5. GCF of the second group is 3. left over is x minus 5. Now inside the parentheses here, we have our two GCFs, and we have our one common factor. So I can write this in our final factored form as x multiplied by x plus 3, which is our two GCFs, multiplied by x minus 5, which is our common factor. And this here is the factored form of the original expression. Next, we're going to look at the factored form, which is exactly where we just ended. We have x times x minus 5 times x plus 3, and we're going to convert our factored form expression back to standard form. So to do this, you need to multiply two factors together at a time. I'm going to start with multiplying these two factors together. So I'm going to distribute my value of x to both terms in the first set of parentheses. This gives me the expression of x squared minus 5x. I'm going to put parentheses around this because I am still multiplying it by that last factor of x plus 3. Then I'm going to distribute my first term to both terms in the second set of parentheses and the second term to both terms in the second set of parentheses. This is going to give me x cubed plus 3x squared. That's these first two terms being multiplied. And then right here, we have negative 5x squared minus 15x. I'm going to multiply any common terms together. The only common terms that I have are 3x squared minus 5x squared. So my final multiplied answer, or standard form answer, is going to be x squared minus, x cubed. I wrote that wrong. X cubed minus 2x squared minus 15x. And you can see for that second example I just did, I multiplied my factored form back to my original standard form. So you can easily convert between these two different forms, and you'll have to do that quite frequently when you are graphing polynomials. One of the biggest things with factored form is to just remember you multiply two factors at a time. Okay, zeros of a polynomial function. So a zero of a function is any value of x that creates a output or an f of x value of 0. Zeros can be real or imaginary. If x is a real number, then x comma 0 is the intercept. And if f of x is equal to x minus 1 in parentheses squared multiplied by x plus 2, then you can identify your zeros as 1 and negative 2. So you set each factor equal to 0. Whatever you get as a solution is your 0. You can write it as an ordered pair and graph that solution. In this first example set, you're asked to identify the zeros and the x-intercepts from the graph. So I'm going to zoom in on the graph and just indicate where the zeros are. Zeros are wherever the graph crosses the x-axis. So we have one right here, 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 and here. If I was to make a table of values, I have my zeros, and then I'm just going to compare what my zeros look like versus my x-intercepts. They are the same point, but you write them differently. So zeros you identify by the exact number. So this one here is at x equals -2. But if you were to write that as an x-intercept, you would write that as -2, 0. X-intercepts are actual points on the graph. The next one that we see is at x equals -1 as a 0. As an x-intercept, it's at -1, 0. Then we have x equals 0, or 0, 0. X equals 1, or 1, 0. And x equals 2, or 2, 0. So just make sure you can identify the difference between a question that asks you for a 0 and a question that asks you for the x-intercept. While they are the same value, you write them differently. So pay close attention to how you're writing your final answer. Example set 2 says, given the following zeros, write a possible model of the polynomial function. You're working backwards here. So if we know what the zeros are, we need to write them in its factored form. And for this one, I'm going to write two solutions. I'm going to write my factored form, and then I'm going to multiply it out to my standard form, just because different directions tell you to do different things. Within each of these examples, you'll see how to do both of them. So for number 1, we have a 0 at x equals -6 and 3. If that's the case, we know that we must have a function that has two factors, one of them being x plus 6, because when you set that equal to 0, you would get x equals -6. And the other factor being x minus 3, when you set that equal to 0, you would end up with +3. This here is your factored form. Now, if you were to multiply this out into standard form, that would tell you to distribute your first terms to your second set of parentheses. When we do that, we would end up with x squared minus 3x plus 6x minus 18, which we can simplify to our standard form equation of x squared plus 3x minus 18. So depending on the directions, you could be writing your function in either form. And if we do the same thing for number 2, number 2 we have zeros at -1, 0, and 4. If we have a 0 at -1, that means the factor is x plus 1. A factor of 0 would be x plus 0. And lastly, a factor of x equals +4, or a 0 of x equals +4 would give us a factor of x minus 4. This factor right here, we wouldn't typically write x plus 0. We would actually write that similar to how we write a GCF. So my factored form is going to be f of x equals x times x plus 1 times x minus 4. And again, we don't write x plus 0, we just write one single factor of x. If we multiply this out into standard form, you multiply two factors at a time. We're going to start by multiplying these first two factors together. That's going to give us x squared plus x, and we're multiplying this by x minus 4. Here's where you distribute. We have x cubed minus 4x squared plus x squared minus 4x. And I can write my final standard form expression after I simplify my common terms. X cubed, negative 4x squared plus x squared is negative 3x squared minus 4x. Again, just be careful whether you are working in factored form or standard form and understand the difference between the two. Next, we're talking about zeros, repeated zeros, and multiplicity. So a repeated zero is called a multiple zero. It's when you have zeros that happen more than once. The multiplicity of a zero is the number of times the associated factor appears. So if you have a factor that appears 3 times, the multiplicity would be 3. A multiple zero has a multiplicity equal to the number of times the zero occurs. So what does this mean? Take a look in this box. So we have zeros that happen more than once. Look at the exponents. We have this here, x minus 1 raised to the power of 3. If we set that equal to 0, we would have x equals 1, and it happens 3 times, so we would say multiplicity 3. This factor is x plus 2. Set that equal to 0, x equals negative 2. The exponent indicates that it happens 4 times, so we would say the multiplicity is 4. Now the multiplicity is specific to the shape of the graph. Next class when we're graphing, the multiplicity will tell you what type of curve to make at each zero. All right, example set 4. Find the zeros and determine the multiplicity of each zero. Number 1. Number 1 is already in factored form, so all I have to do is set each factor equal to 0. X squared is x equals 0. This factor happens 2 times, so we would say it has a multiplicity. I'm going to abbreviate this as MULT, multiplicity of 2. This factor, x minus 1, has a 0 at positive 1. This factor only happens once. The multiplicity is 1. And our last factor has a 0 at positive 2, occurring only once, so the multiplicity is 1. Number 2 is in standard form, so in order to find the zeros, I would have to factor this. I have x squared minus 6x plus 9. This one has, or think to yourself, what 2 factors multiply to equal positive 9 and add to equal negative 6? And that would be negative 3 and negative 3. This factors out to x minus 3 times x minus 3, and we're solving for this, so we set them equal to 0. Because we have 2 of the exact same factors right here, we can rewrite this as x minus 3 in parentheses squared equals 0. If I set that factor equal to 0, we know that x equals 3. This factor happens 2 times, so we would say the multiplicity is 2. For the next example, we want to write a polynomial in factored form that has the zeros listed here. So I'm going to use the zeros that are listed. I'm going to identify the multiplicity as an exponent, and then I'm going to write my function in factored form. So for this first one, we have a 0 at x equals -2 with a multiplicity of 1. Well, if the 0 is at -2, that means the factor must be x plus 2. That way, when you set that equal to 0, it would be equal to -2. And if the multiplicity is 1, that means the exponent of that factor is 1. For the next factor, we have a 0 at x equals 3, telling us that the factor must be x minus 3. And because the exponent is 2, or because the multiplicity is 2, that tells us that our exponent is going to be 2. That means that factor happens 2 times. And for our last factor, we have x minus 5. Because the multiplicity is 3, that tells us the factor is happening 3 times, or you could write an exponent of 3. Of course, if you have an exponent of 3, that's telling you precisely that the factor is occurring 3 separate times. But we wouldn't write it out like this because that's a waste of our time. We would literally just write it with an exponent of 3, and that's all you would have to do. So once you identify what your factors are, we're just going to write this function in factored form. I'll use function notation. F of x is equal to, we have our first factor of x plus 2 multiplied by x minus 3 squared, because there's 2 of those, and x minus 5 in parentheses cubed, because there are 3 of those factors. And this is your function in factored form. And multiplicity on the graph. This is more important next class, but real quick. Even multiplicity indicates that the graph touches or turns at the x-axis or at the associated 0. If we look at this graph, there's a 0 right here. The graph comes down, touches that point, heads back up. This graph, we have a 0, comes down, touches it, heads back in the same direction. If the multiplicity is odd, that's telling us that the graph is going to cross through at the associated 0. So in this graph, there's a 0 here, and the graph goes right through that point. There's a 0 here, and the graph goes through that point, leveling off a little bit. So odd multiplicity crosses the x-axis, even multiplicity does not. Now on all of these examples that you have here, you can see that some of them have a little bit more of a leveled off curve instead of just going straight back in the same direction, and same thing here. So the higher the degree of the function, the more of a leveled location you will have at the 0. And leveled meaning it comes up, levels off, goes back in the same direction. Okay, for the last example set, we need to use zeros and multiplicity and identify what's going on from the graph. So number one, we have this curve here. The zeros are going to occur where the graph crosses the x-axis. So I'm just going to mark my 2 zeros. So we can either call these zeros or we can call them x-intercepts. I know that one of them happens at x equals -2, and I know that the other one occurs at x equals +2. So now I need to determine the multiplicity, and the multiplicity is determined by either crossing through the x-axis or turning at that point. So the easiest way to determine this is to draw over the graph. If I draw over the graph, am I drawing through the x-axis or am I turning at the x-axis? And you can see right there, I just drew right through that point. I'm following along, and I'm going to draw right through this point again. Now, if I was comparing to something that would turn, that means this graph would come up to the point and then turn back in the same direction. That is not the case here. So when I traced over the graph, I drew straight through each point. Now, the straighter the line, the lower the multiplicity. Because I'm drawing straight through them, I know that I have an odd multiplicity. Because it's a straight-ish line, I'm going to say that the multiplicity, abbreviated as MULT, the multiplicity is 1 because the graph crosses. And for x equals 2, this also has a multiplicity of 1, and the graph crosses through there as well. Number 2, we have a 0 here, here, and here. So I'm indicating everywhere where the graph either touches the x-axis or crosses through the x-axis. So we have a 0 at x equals -2, at x equals 0, and at x equals 1. If I trace through the graph, right here I'm drawing straight through at this point, so I know that multiplicity is going to be an odd number, a low odd number such as 1. Then I come back down to this point where it touches the point but heads back in the same direction. So that's going to be an even multiplicity, such as 2. And then I'm going straight through the point again. So at -2, we're crossing through the x-axis. We're going to say multiplicity 1 because it crosses. At 0, the graph bounces. So we're going to say multiplicity of 2 because it bounces, or I'm going to say turns. And that 1 crosses through again. Multiplicity 1. Okay, and for the last on your own section, I'll actually go through this table with you because it's important for graphing and understanding what each part is. So we have a function, f of x is equal to 3x plus 2, in parentheses cubed, times x minus 1, times 2x minus 4 in parentheses squared. Starting at this first factor, if I set that factor equal to 0, I'm going to end up with 3x equals -2, or x equals -2/3. This is called a 0. So x equals -2/3. The multiplicity at this point is asking us how many times does that factor occur? That factor happens 3 times. The x-intercept is asking for the actual location of that point. So where are you going to plot that point on the graph? and you would plot a point at -2/3, 0. And the behavior at the x-intercept, meaning does it cross or turn? And because the multiplicity is 3, that's an odd number. That tells us that it's going to cross. So, zeros and x-intercepts are essentially the same thing. One of them is the location on the graph. One of them is just the answer. Multiplicity tells you what the behavior is on the graph. Okay, the next factor, x minus 1, set that equal to 0. Your solution would tell you that x equals 1. This factor only happens once, so the multiplicity is 1, which is an odd number. On the graph, we would plot this point at 1, 0. And because it's an odd number, it would cross at the x-axis. And the last 0 occurs at 2x minus 4. When we set that equal to 0, we would have x equals 2. This factor has an exponent of 2, so we know that the factor occurs twice. 2 is an even number. This point is located at 2, 0. And because it's an even number, it turns at the x-axis. All right, after this lesson, you have several tests and tools to aid in graphing polynomial functions, which is what we will be doing on tomorrow's note sheet.